Okay, the next topic I want to talk about is continuation passing style. This is a style of programming that lets you turn any non-tail call into a tail call. Now, when we talked about tail recursion, we already covered a little bit about this, right? About how when we had non-tail recursion, we couldn't simplify it. But if we had a tail recursion, then we didn't have to grow the stack as we did the recursion, right? Because the idea of tail was the last call was that recursive step. So we didn't have to deal with it. So the parent caller doesn't need to sit around and wait for the child to actually return its value. It could just return it straight up to its previous parent. For instance, right, we have our factorial function, right? This takes in an n, which is an int, and returns an int. And what does it look like? Well, if n is less than or equal to 1, then we just want to return 1. Else we want to return n times factorial of n minus 1. Right, and this didn't necessarily look look like a non-tail call, but it is because, right, we are waiting for the value of fact of n minus 1 to return before we can multiply it by n and pass that back up the chain. Right, so it's in fact a little better to write it like this. Val v is equal to factorial of n minus 1, and then n times v is what we're returning. Right, and we saw a way that we could get around this by essentially passing along a accumulator, right? So we did it like this. We had n as an int, and accumulator is an int, and then we return an int. And what did we do? Well, if we had a base case n is less than or equal to 1, then we're just going to return the accumulator. Else, we're going to return, well, we don't need the two steps, right? We're just going to call factorial, this new version, with n minus 1. And then this accumulator is going to pick up this computation here. So we're going to multiply n times accumulator. Right, and we saw that as we go through this, this accumulator picks up all of the different numbers that we need to multiply. And when we get down to the base case, we basically already computed the factorial. So this is pretty easy because, right, the remaining computation that we had to do was just multiplying a number. But we can in fact do this for any amount of extra computation. So that's what we're going to do with continuation passing style, is sort of a one-size-fits-all solution that takes any function that is non-tail and turns it into a tail call by packaging up all of the remaining computation into a new function that we then pass on to that final tail call. So I'm going to show an example of how we do this with this factorial function, and then we can kind of see exactly how this works. So the key idea here is all of our functions. So we have, say, foo, and we have, which let's say takes in an int and returns an int. And we also have bar down here, which maybe takes in a string and returns a string. Right, in our normal world, we'd have these, and then in our new world, we'd have something like foo underscore CPS, which takes in an int, and now instead of, right, in our factorial, we had just an accumulator, which was an int, but now we're going to have a function, which is called a continuation. And it's going to take in whatever foo returned, right? Foo returns an int, so it needs to take in an int, and it's going to return something. Typically, we'll leave it sort of ambiguous. We'll talk about that when we can talk about generics. But for right now, let's just say it's an int. And then this whole thing returns an int. Likewise, bar down here, we'll have bar CPS, and that's going to take in a string. And then let's assume this is an int as well. It returns an int. Then our continuation will also, it takes in an int, and it will return, let's say, a string. So the whole thing returns a string. And where does this k come from? It's going to come from whatever calls foo CPS. So whatever parent function called foo CPS is going to hand in all of the extra work that needs to happen after foo gets called. Right, so the idea is foo originally, you'd give it a number and then it does some work and it returns a number. And then whatever called foo, right, takes that number and does something with it. And what that something that we do is going to be encapsulated in this continuation, K for continuation. And so that's why this should be an int. And if bar returns an int, this should be an int. So yeah, let's see how this works on factorial. Right, so we're going to write up fact CPS, and it's going to take an integer and a continuation. And what should it do? It should, if n is less than or equal to 1, we want to well, do whatever function or whatever its parent call did, right? We're going to pass k applied to 1, right? This is one of the key points in continuation passing style is we never return a value directly. We always call a continuation on it. Right, because the idea is the continuation is whatever extra computation my parent call needed me to do for it. So I'm going to make sure that I take care of that on whatever my final result should be. So yeah, we have our base case. So if n is less than or equal to 1, we're going to call the continuation on 1. Else, right, what are we going to do? Well, we're going to call factorial CPS on n minus 1. And then we need to come up with a new function here, right? A continuation that we're going to pass to fact CPS. And it's going to be whatever is going on after the call, right? So the first time we make that call, we're going to package up all of this. I mean, there's only one line here, but there could be a lot of computation going on here, right? We're going to package that all up into its own named function or anonymous function, and we're going to pass that on to the child call to have them take care of it for us. And so what do we want to do? Well, it's going to be an anonymous function. So it's going to take in v. V is going to be whatever fact CPS, this subcall, this n-1 call, whatever it needs to return, right, because it wants to call the k on it. And it's going to, what is it going to do? Well, we want to make sure that we do whatever my parent wants us to do. And then we're going to do whatever we want our child to do, right? So the inside of this is our leftover computation. And the k is our parent's leftover computation. And that's it. Right, so this is the continuation passing style for factorial. Let's walk through a small example and see exactly what's going on and how this works. All right, so what happens if we have, say, fact CPS on 5 with, so we always have to, the very first call, we have to figure out what is that continuation going to be. Right, what's that starting continuation? And we can use the identity function, right? All it's going to do is pass back the value, right? So this is basically, there's nothing else to do, so I'm going to just pass that in as my generic starting continuation. So what does this do, right? Fact CPS on 5 with this continuation, well, we look through here, 5 is definitely bigger than 1, so we end up calling fact CPS on 4 with a new continuation. Let's call it K1. Well, what is K1 going to be? Right, we sort of wrote it down here. K1 of V should be, well, let's call this K0 to start with. going to be k0 of whatever n was for this call, right? So that's going to be 5 times v. Right, we're just following this definition. Okay, now CPS 4, what's it on K1, what's it going to do? Well, 4 is bigger than 1, so we're going to end up calling fact CPS on 3 with a new continuation K2. Right, and what's that continuation going to be? Well, it looks like this. I'm going to take my parents' continuation, that's K1, and I'm going to do whatever else I need my child to do, which is going to be 4 times v. So K2 of v is going to be K1 of 4 times v. This one likewise is going to call fact CPS of 2 with K3. And what's K3 do on of some value v? Well, it's going to do what its parent needs it to do, which is K2. And then we do whatever leftover we need here. So 3 is our n in that case, and we're going to do 3 times v. Finally, fact CPS 2 calls fact CPS 1 with K4. And what's K4? Well, it's basically the same thing that we've been writing up before, right? It's going to be K3 with, on the inside, 2 times v. Okay, now what does fact CPS 1 K4 do? Well, if n is equal to or less than or equal to 1, we just call whatever the k is we passed in on 1. So this is going to call K4 on 1. What does K4 do on some value v? Oh, it calls K3 on 2 times that. So this is going to call K3 on 2 times 1, right? Or I'm just going to simplify it to 2. What does K3 do? It's defined up here. K3 on some number. It's going to call K2 on 3 times that number. So this is going to be K2 times 6, or K2 applied to 6. What does K2 do? K2 on a number calls K1 on 4 times whatever is inputted. Right? So this is going to call K1 on 6 times 4, which is 24. And K1, what does K1 do? K1 takes a number and applies K0 to 5 times that number. So we get K0 of 120. Right? And then what is K0? I said that this was the identity function, right? So all it does is return the number. So K0 is just going to be, K0 of 120 is just going to be 120. And this is the process that we have for CPS, right? So the idea is each one packages up all of the stuff it needs its child to do. And then once we get to the very bottom of the chain, all of that extra computation gets completed by the final call here, right? And all of this is our tail calls. The whole thing is a nice tail call, so we don't actually have to even keep this all in a stack. We can just keep on removing them from the stack and calling these all in one single long line. And that's the power of it, is we can take any function that we want and do this to it. For instance, our eval function, right, that was a highly complex recursive call with a lot of subcalls going on, right? If we evaled some expression that had an E1 and an E2 in it, we'd have to do both of those like plus, right? We have to eval E1 and then we have to eval E2. So how can we do this sort of CPS transforms to make sure that eval doesn't create this huge recursion tree, but instead has a really nice long single recursion line that we can then optimize. We're going to get into the details in the next video.